Hello, my name is Paula Scotti. I'm the current president of the American Astronomical Society. I want to welcome you to the presentation of the 21st Annual Gruber Cosmology Prize, which the AAS is very happy to be able to host at our meeting this year. The Gruber Foundation gives three $500,000 prizes each year in the fields of cosmology, genetics, and neuroscience. Sarah Rea, the executive director of the Gruber Foundation, is now going to give you some more information about the Gruber Foundation and its prize program. Sarah?
Thank you, Dr. Scotti. We are pleased to present the prize as part of the AAS meeting. Let me just share my screen and start my PowerPoint. Come on. There we go. The Gruber International Prize Program was established in 2000 and recognizes achievements and discoveries that produce fundamental shifts in human knowledge and culture. While we are here to honor Lars Hernquist and Volker Springel, let me mention that they joined Bonnie Bassler and Friedrich Bonhoeffer, Corey Goodman, and Mark Tessier-Levine on our 2020 roster. Please note that nominations to the 2022 Gruber Prizes will be open from this spring until December 15th, and that we encourage nominations that reflect the breadth of the fields and the diversity of those working within them. Before we return to cosmology, I simply must acknowledge our co-founders, Peter and Patricia Gruber, whose combined vision and leadership established the International Prize Program, and whose care in doing so gave it the legs to stand on its own. The Cosmology Prize is presented in conjunction with the International Astronomical Union, a partnership that has guided our efforts since our earliest days. It is my pleasure to introduce their president, Aveen van Dieschuk.
Thank you very much, Sarah. The IAU is very pleased to have collaborated on the Gruber Cosmology Prize since the prize's inception in 2000. The IAU has an advisory role in the constitution of the Selection Advisory Board. And as part of the collaboration, we are actually delighted to receive an annual grant of $75,000 to be awarded to postdoctoral fellows from around the world so that they may pursue educational research at a center of excellence. Now, this research and this money can be divided among 2 or 3 candidates, and it enables them to do their research, their travel, collaborations, publications, but as we will see, also in other ways. Scientific quality is the prime criterion, but we also give preference to countries in dire economic conditions. And you see already here from the previous winners over the years that we have been very successful in enhancing the diversity and help us in that way build a diverse and thriving astronomical community around the world. So let me actually introduce to you this year's 3 TGF winners. The first one is Anupam Bhaja. He works actually on pulsating stars, both to study the 3D structure of the Milky Way and also as a cosmological probe. He got his PhD in Delhi in India, then was a postdoc in Kavli Institute in Beijing, and is now on an East Asian fellowship, joint between Japan and Korea, clearly all around the world. And he plans to use part of his TGF grant to support visits of students from universities like him that with limited resources. The second candidate is Gabriela Calistro Rivera. She actually works on multi-wavelength studies of galaxies and AGN at high redshifts. She has Peruvian nationality. She got her PhD in Leiden, the Netherlands, and is now on an ESO fellowship in Germany. And she will actually use part of her TGF grant to continue her work, jointly actually with the IAU, on training teachers in rural areas in Peru. And she will also enhance her activities as a science ambassador within the ESO member countries. And the third candidate winner is Yannis Diodakis. He works on blazars and trying to understand how these brightest objects in the universe actually shine. He got his PhD in Crete in Greece, then moved to Stanford on a fellowship and is now at Turku University in Finland. And he will actually establish a visitor program to increase the diversity and collaborations with underrepresented countries. So I've just given you a taste of the success of this TGF Fellowship program. We're really delighted that this has been established, and we thank the Gruber Foundation for it. Back to you, Sarah.
Thank you, Dr. Van Dieschuk, for joining us today. Our relationship with the IAU is invaluable. Lars, Hernquist, and Volker Springel were chosen for the 2020 prize by a distinguished selection advisory board nominated by the IAU and its affiliate organizations. The members of this board are James Evans, Wendy Friedman, Paul Ho, Robert Kennicott, Angela Olento, Franz Pretorius, Jean-Luc Pouget, Martin Reeves, and Linda Taccone. We sincerely appreciate the knowledge, commitment, and enthusiasm that the advisors bring to the judging process. Let me now invite the chair of this board, Rob Kennicott, to present the official citation to the prize and introduce the scientific accomplishments of our recipients. Dr. Kennicott?
Thank you, Sarah. Let me read from the citation. The Gruber Foundation is pleased to present the 2020 Cosmology Prize to Lars Hernquist and Volker Springel for their transformative work on structure formation in the universe and development of numerical algorithms and community codes further used by many other researchers to significantly advance the field. The contributions of Hernquist and Springel have led to profound insights spanning billions of years of cosmic evolution, including simulations of the growth of early density fluctuations through to present-day galaxies, and the influence of galaxy mergers on star formation and the close coevolution of supermassive black holes with their host galaxies. That's the citation. I'll add a few words of my own. I think every one of us is aware of the profound impact that computational astrophysics and simulations have had on astrophysics as a whole, and no less than in cosmology. 10 years ago, this prize was awarded to Davis, Evstathiou, Frank, and White for the development of the cold dark matter cosmology, and much of that work, of that breakthrough, rested on n-body simulations, state-of-the-art at the time. In many ways, this award can be regarded as a culmination of that work, not only extending the art of n-body computations, but adding hydrodynamics, feedback, radiation physics, and the other relevant processes, as you'll no doubt hear about during the talks which are going to follow. The result of that is now a theory, as the citation states, that literally links the earliest quantum fluctuations in the Big Bang to the whole sequence today. It's just a truly remarkable achievement. Now, we're all aware as well that many, many individuals are responsible for this triumph. We can recognize two with this nomination and award, and I think the board felt it was especially appropriate to recognize Lars and Hernquist because their work embodies not just top shelf computational astrophysics. I mean, these folks can code for sure, but it's the marriage of that brilliance to brilliant astrophysical insight which drove the design of the simulations, the experiments, their execution and their interpretation. And finally, last but not least, their extraordinary generosity in making their codes available to all of us, which has multiplied the impact of their work immeasurably. So that's those are my remarks. And so with that, I ask Lars and Volker if you could join us, which means switching on your cameras. And you will receive the prize. Sarah?
I just would like you to point out your prize pins. You're wearing them already since I'm not there to put them on you. We're so happy to have you on the roster, and Let me just tell the audience that after the honorary lectures, prize advisors Wendy Friedman and Martin Rees will moderate a discussion with them. You may submit your questions via the Zoom Q&A function at any time, so feel free to send them in during the lectures. And without further ado, let's hear from our recipients. Congratulations.
Yeah, thanks a lot also from my side. Let me first say that receiving this prize is an incredible honor for me, and this is also highly motivating and uplifting. I am deeply thankful to the Gruber Foundation for the enormous support of science in general, and the field of cosmology in particular. And I hope that many other scientists can benefit from your continued support and encouragement in the future. In the next 25 minutes, I'd like to give you a broad, in part historical, perspective on the role of cosmological simulations for the field. In particular, I will recap a few key steps in my own work and that of Lars Hernquist that I feel were important to advance cosmological simulations of the universe to their current state. I'll focus mostly on our own contributions on today's occasion, so please apologize if I don't explicitly review all the many important contributions made by other colleagues in the field. After my remarks, I'll hand over to Lars for the second half of the talk. He will focus more on the state of the art in the field with respect to hydrodynamical simulations of galaxy formation. As you know, in cosmology, we have arrived at a standard model where in particular the initial state left behind after the Big Bang has been measured with exquisite accuracy. The model that has emerged is, however, exceptionally strange. We got very used to it, but it is still deeply challenging us with the implication that most of the matter in the universe is not made up of ordinary stuff, namely baryons, but rather from unknown elementary particles, which we call dark matter. And arguably even worse is the existence of a dark energy field that acts as a kind of anti-gravity and now drives space apart at an accelerated rate. Can complex galaxies like the Milky Way really form from these initial conditions out of this strange matter-energy composition? To answer these questions, one would like to compute forward in time for 13.5 billion years, what emerges out of these cosmic initial conditions. For the dark matter, one then has to solve this system of equations, the so-called Poisson-Vlasov system. It describes the phase-space evolution of collisionless dark matter, and it is an integral partial differential system of equations. Despite their formal simplicity, these equations can only be solved analytically in a few simple cases. But one can discretize the equations by sampling from the phase-space distribution. Then one obtains the so-called n-body problem, where the task becomes to follow the orbits of n point masses under the mutual self-gravity. This is conceptually a huge simplification, except that the number of bodies needs to be very, very large. And that makes it computationally difficult. For the helium and hydrogen gas, one can apply the Navier-Stokes equations of fluid dynamics. Actually, even ideal gas dynamics is in most situations adequate, because the viscosity of the thin cosmic gases is extremely low. The fluid equations can also be discretized to allow a numerical computation. Here one often uses a mesh-based representation, similar to a pixelized image, or one can also use particle-based representations, for example, in smooth particle hydrodynamics. I will come back to a comparison of these schemes later on. In addition, fully describing galaxy formation requires further PDE systems, accounting for physics such as radiative transfer, magnetic fields, or radiative cooling chemistry. The nonlinear complexity arising from these coupled equations is what makes cosmic structure formation such a complicated phenomenon. Nowadays, we have powerful supercomputers that can help enormously to tackle this problem. Machines like the one shown here can carry out around 10 to the 16 floating point operations per second. So every person on Earth would have to do 1 million multiplications or additions per second to match this performance. On the supercomputer, this is distributed onto the shoulders of about 100,000 cores. This means it is a parallel machine where the calculations need to be distributed such that the different processors can all work simultaneously on the problem. This distribution of the work is non-trivial, especially not for the universe, where the long-range nature of gravity couples everything tightly together. So one needs a scientific code to put onto the supercomputer. Here, I like to draw an analogy to our large telescopes. Without sophisticated instruments to put on them, they would be quite useless. And it's just the same with the supercomputers, where you need a code as your instrument. Code development has therefore been crucial to advance numerical cosmology. My own work on this has been based on seminal contributions by Lars and collaborators in the form of their 3SPH code, where smooth particle hydrodynamics was combined with a so-called tree algorithm for computing gravity of an n-body system. In the gadget code, developed as part of my PhD thesis, this approach was parallelized for distributed memory with MPI. In 2005, I published an improved version of the code, Gadget 2, and made it publicly available. It has seen widespread use in the community since then and allowed for considerably larger calculations than possible up to this point. Similarly, for the next iteration, Gadget 3, this code also spawned a large number of developments by other people based on it. On the slide, I just mentioned the Eagle version of the Gadget code and Gizmo as two examples. Over the last decade, I myself focused on developing a novel moving mesh approach for discretizing cosmological hydrodynamics called a repo. Yet Gadget still lives on. We just recently produced a new generation of this venerable code. These codes all have over 100,000 lines each. This movie shows a zoom into the Millennium simulation done with Gadget 2. It was the first calculation that could use more than 10 billion particles and profoundly advanced our understanding of how the nonlinear cosmic web forms out of the tiny density fluctuations at early times. I apologize if the video is a bit jerky on your end. This is because re-encoding the movie via Zoom with a high frame rate is difficult. But I hope you can still see the beautiful network of intersecting filaments, which connect more or less spherical blobs of collapsed dark matter, which are the places where galaxies form. Among other things, this calculation allowed the construction of artificial galaxy surveys based on the computer-evolved universe. The clustering pattern of the predicted galaxy distribution can then be compared to the real universe, like it's done here in the diagram. The pie diagrams in blue show real galaxy surveys, the ones in red, the Millennium simulation, for comparison. And the reassuring result of this comparison has been that the lambda CDM universe indeed predicts large-scale structure in very good agreement with what is observed. The utility of such cosmological simulations also becomes clear if one looks at their use in the literature. In fact, the Millennium simulations data has been used in nearly 1,100 research papers thus far. Simulations also help to uncover the existence of a plethora of dark matter substructures embedded inside individual virialized dark matter halos. This movie shows the assembly of the dark matter making up the halo of a typical Milky Way-sized galaxy. The theoretical prediction is thus that we are surrounded in our own galaxy by a sea of dark matter subhalos. Some of them are naturally identified with the dwarf galaxies in the Milky Way, like the Magellanic Clouds or fornax. But whether or not this level of small-scale structure is consistent with observations is a hotly debated question to this very day. Dark matter substructures are also places where dark matter could possibly self-annihilate. To precisely compute how much annihilation radiation one can expect from dark matter, One needs to determine both the abundance and concentration of halos down to the smallest halos that exist. In recent work, this has in fact become possible. In simulations with the Gadget 4 code that we published last year, dark matter substructures have been resolved over a dynamic range of 30 orders of magnitude in mass. This has been accomplished by hierarchically refining assumed region in a large box calculation, as depicted in the image. At the end, the smallest existing halos, roughly of Earth mass, have still been resolved with order 1 million particles each. This allowed a precision determination of the dependence of halo concentration on halo mass over the full mass scale of existing objects, from rich galaxy clusters to halos more than 20 orders of magnitude less massive. We can thus conclude that at least as far as the dark matter is concerned, simulations can now accurately characterize the full spectrum of nonlinear structures that exist in a lambda CDM universe. Let me now pause for a moment and reflect on why I think simulations have become an indispensable tool in cosmology. As we have already seen, they deliver solutions for complex equations that we otherwise could not solve. We can also do numerical experiments in the computer, for example, letting two galaxies collide and see what happens. Such experiments allow us to test specific physical hypotheses. And sometimes we can even discover something unexpected in these simulations. Also, visualizations, such as the ones I've shown you, help to provide much needed physical intuition. The dark matter is a primary example, of course, because the real beauty and complexity of the geometry of the cosmic web is all hidden to the naked eye. And because of these features, it is perhaps unsurprising that the impact of simulations in astrophysics has in fact steadily grown over the years. One can see this, for example, through the growing fraction of papers that rely on simulations in the refereed literature. Finally, let me also stress that I like to view simulations as a powerful tool of a deductive approach to science. This contrasts with more empirical, data-driven methods that are gaining much popularity at the moment and which represent more of an inductive approach. In practice, of course, both approaches need to work together closely. Unlike dark matter-only simulations, hydrodynamical simulations, which I'd like to discuss now, address the full cosmological problem, including the baryonic sector. They, therefore, also need to predict the occurrence of stars and of supermassive black holes. It is no surprise that this makes the problem much harder. Indeed, if we go back a good 15 years ago, when Lars and I started to work on this together, the state of affairs was really quite desperate. Even simulations at low resolution vastly overpredicted the cosmic star formation rate. They could not prevent cooling gas to collapse away under self-gravity and to make much more massive galaxies than seen in the universe. In addition, the outcome of the calculations showed a strong dependence on numerical resolution, effectively precluding quantitatively reliable predictions. To work around this impasse, Lars and I proposed an explicit subgrid model for the treatment of the interstellar medium in cosmological simulations. This made the simulations well posed from a numerical point of view. Still, the required dynamic range for cosmic structure formation could not be addressed in a single calculation. We overcame this issue by developing a simulation strategy that involves several different box sizes, and for each of them, a systematic convergence study. This allows one to infer a combined fiducial result at a converged resolution that covers then the full relevant dynamic range. Here are just some of the equations describing this simple subgrid model at the time, which gave rise to an effective equation of state for the interstellar medium, which is shown here on the right. And having such a model in hand, we could then work out analytically what its free parameter, the gas consumption timescale, would have to be to match the observational relation between gas surface density and star formation density in large spiral galaxies. This observational relation is, of course, known as the famous Kennicut law. And lo and behold, if we then simulated a galaxy with this model, It reproduced the observational Kennecat law, as you can see in this diagram on the right. This confluence of numerical and analytical understanding is of course helpful for building up trust in the correctness of the numerical simulation codes in the first place. Using our technique to run a whole simulation series, which you see schematically depicted on the left, we could then go ahead to make numerically converged predictions for the cosmic star formation rate density of the universe throughout its evolution. But before getting to this, let me show you here on the right the supercomputer we used at the time. This was actually a machine we put together ourselves in the basement of the C of A. When I was postdoc in Lars' group at the time, doing some of these simulations, it was not uncommon for us to go down into the cellar when the code had crashed because of a node failure. We would then pull it out from one of these racks and try to somehow repair the particular node, or at least to recover its hard drive with simulation data on it, and then plugging it into a still functioning node in order to continue. At the end of the day, we could then come up with a composite result for the cosmic star formation rate density and also develop fairly clear analytic understanding of how this arises. The match with observational data we obtained was encouraging, but hardly perfect. So it soon became clear that some key physical ingredient was missing in these early simulations. Supermassive black holes were a primary suspect for this. One reason to consider them is that quasars put out an enormous amount of energy when they shine. For a typical activity period of a luminous quasar, the radiated energy amounts to of order 1 billion supernova explosions. And averaged over the whole universe's lifetime, one can easily estimate that the energy released by all supermassive black holes is of the same order as that of all supermassive supernova explosions combined. So energetically, the black holes can easily compete with the supernova feedback. The big question, however, is, does this energy do anything significant to the quasar host galaxies? To look into this, Lars and I, together with Tiziana Di Matteo, carried out a sequence of simulation studies starting in 2005. In hindsight, I consider them the most daring calculations I've done in my career thus far. Basically, we placed massive black holes in the centers of galaxies and assumed that they could feed on the local gas with an accretion rate simply estimated with Bondi-Hoyle-Littleton accretion. And in addition, and this is arguably the boldest assumption of them all, we assumed that the accreting black holes would couple 5% of the liberated energy thermally to the surrounding gas. With this, we could then carry out numerical experiments of colliding galaxies, where during the merger, gas would be driven into the central galactic nuclei, lighting up quasars that are initially buried there. The black holes then grow in mass to a point where the remaining gas would be expelled by energy feedback, leaving behind a red and dead spheroidal galaxy. Interestingly, this type of self-regulated growth of black holes could explain the observed scaling relations, for example, between black hole mass and stellar velocity dispersion. It also helped to produce red enough colors for the merger remnants, making them consistent with the so-called red sequence. Since then, the conjecture of AGN feedback has become widely accepted as a central piece of physics in the life of massive galaxies. Finally, to start introducing the more modern developments, let me show this figure from a highly influential paper led by Oscar Argertz in 2007, co-authored by many numerical astrophysicists, including myself. This study compared different cosmological hydrocodes when applied to a well-defined problem. The problem illustrated here is what is now famously known as the blob test. Here, a supersonic wind blows over a cold, dense cloud of gas set into a hotter background medium. The wind is slowed down by a shock ahead of the cloud and then streams around the obstacle. The shear flows at the sides of the cloud should excite fluid instabilities that with time disrupt the cloud. The problem now is that particle-based hydrocodes, like the two shown on top, give a very different result from mesh-based calculations, like the 3 examples shown in the bottom rows. In the particle codes, the cloud is never fully dispersed and mixed with the wind. This serious discrepancy has been very bad news because it showed that the numerical techniques for hydrodynamics actively used in cosmology at the time suffered from serious systematic errors. This was very chilling for me and compelled me to develop an entirely new discretization approach. In fact, it led to the ARIPO code, which uses a fully adaptive moving mesh constructed as a Voronoi tessellation from a set of mesh generating points. The mathematical properties of the Voronoi tessellation ensure that the mesh can move continuously with the flow without ever breaking down due to mesh twisting, even in situations where there is shear, like in this movie. With the clear geometry of the mesh cells in hand, one can then use Godunov's method and apply Riemann solvers to compute numerical fluxes across all mesh interfaces. The accuracy advantage of this approach resolves the defects seen in the blob test and addresses a number of other numerical shortcomings of cosmological codes when applied to galaxy formation. And this improved accuracy indeed makes a difference. Here you see a small cutout from a cosmological simulation comparing the gas distribution in 2 cases. Once obtained with the modern moving mesh code in the top image, and once computed with the older particle-based technique on the bottom. The physics is the same here. The initial conditions are the same, and the number of resolution elements is the same as well. Yet the disk galaxy that has formed is far better defined and less noisy in ARIPO than it comes out with Gadget. Still, I need to also point out that the effects due to feedback can be even stronger than these code differences. So they certainly also need to be taken into account. The advantages of ARIPO now help in studies of a variety of problems in astronomy, not only for galaxies, but also in stellar astrophysics and cosmic logical structure. Over the past 10 years, Lars, Hernquist, and I, and many collaborators of us, have used this code to usher in a new generation of cosmological hydrodynamical simulations. Lars will continue momentarily to tell you about this. But before he does that, let me just briefly acknowledge my collaborators. I owe big thanks to many colleagues, more than I can name here. Throughout my scientific career, I have tremendously benefited from scientific discussions and support, in particular by Simon White, Carlos Frank, and Lars Hernquist, but also by many others. In fact, I've been incredibly lucky to have had a chance to work on many projects with extremely talented people in the field. I just mentioned a subset of them here on the slide. And I want to thank all my students who are a great source of inspiration for me and make research fun. And last but not least, I've been really fortunate to have received support for my work by funding agencies and supercomputer centers that all hold basic research in high regard. In my case, this has primarily been the Max Planck Society, the German Science Foundation, the European Research Council, the Klaus Tschira Foundation, and the 3 main supercomputer centers in Germany. Thanks a lot to them. And now I quickly hand over to Lars.
Thank you, Volker. So let me start to share my screen. Okay, so today I wanted to describe to you work that Volker and I have been involved with for the past 10 years or so. And the goal here is to use large-scale cosmological simulations to try to gain some insights into how galaxies form and evolve over cosmic time. So this goes by the name of two big projects that we've been involved with called Illustrious and Illustrious TNG. The work has been very laborious in nature and has involved the contributions of many collaborators to these projects. In particular, the names that I've listed here are the people who are involved from the beginning in developing the models and carrying out the simulations I'll talk about today. And I should particularly acknowledge the contributions of Mark Vogelsberger, Annalisa Pilipich, and Rainer Weinberger, who did a lot to develop the physical models that the simulations are based upon. So let me just start with a little bit of an overview. So what is the goal of this work? So we'd like to ultimately develop a fully predictive theory of galaxy formation. So this is a field where the observational side has been ahead of the theoretical one for quite a long time. And so this has led to a situation where we have a huge amount of data that needs to be fully digested and understood. In particular, surveys of galaxies, observations of individual objects. And we know now that galaxy formation also means understanding the origin of stars as well as supermassive black holes. So these are issues that all need to be addressed and properly understood theoretically. Furthermore, we'd like to relate luminous galaxies to the underlying dark matter distribution that would allow us to test the basic paradigm of structure formation that Volker mentioned in his talk. And finally, to interpret data that will be coming in the near future from high precision cosmological surveys that attempt to measure properties of the universe to 1% precision or better. This is quite a long-standing problem that's been with us for as much as 100 years, dating back to the discovery of the expansion of the universe. I'm not exactly sure when the theoretical study of galaxy formation started, but I'd like to highlight the work from 1962 by Egan, Lindenbell, and Sandage, which was one of the first quantitative models of how galaxies might form in the universe. And their idea was that galaxies form through the collapse, the monolithic collapse of giant gas clouds from the intergalactic medium. We know now that things are much more complicated than this, based on discoveries that have been made over the past 60 years. But in spite of the efforts and the progress in the field, we still haven't arrived at a completely predictive theory of galaxy formation. And so the important discoveries that have complicated things considerably are, for example, the role of dark matter, the importance of galaxy mergers, which occur naturally because we think our universe is hierarchical in nature. Finally, especially over the course of the past 20 years or so, it's been realized that galaxies contain supermassive black holes at their centers, and these supermassive black holes can provide energy that can affect the distribution of gas throughout the entire galaxy, affecting its future star formation. So I like to think about this as the good, the bad, and the ugly in terms of developing a theoretical model for galaxy formation. So the positive aspects are that we have a well-defined framework to work from, which Volker mentioned in his talk, in that we have an underlying standard model for the universe and its constituents. And so based on that, we can generate well-posed initial conditions that we can run forward in time, in principle, to understand how what we see came about. The evolution of the dark matter is well understood. It's gravitational, at least on cosmological scales. And on top of that, we think we understand the physical laws that govern the other components of the universe, in particular the baryonic component that makes up the luminous parts of galaxies. Unfortunately, things are quite a bit more complicated because we need to account for not just the dark matter, but the baryonic physics that gives rise to ultimately how galaxies form. And so these physical processes are much more complex than the dark matter. This is a point that's been emphasized significantly by Martin Rees. And the point is that although we know what the physical laws are that govern the evolution of the baryons, we don't know how they manifest themselves or interact with each other in the context of galaxy formation. On top of that, the problem is intrinsically nonlinear, especially the gas component of the universe, and there aren't any obvious symmetries that we can use to reduce the problem significantly. Finally, there's a huge problem with the dynamic range that we have to consider in length, mass, and timescales, as I'll show in a minute. And so all these things mean that even though in principle things are well formulated, the baryonic evolution of the universe is problematic at this point. And so that's illustrated by this figure here on the right. It shows the number density of objects versus their mass in the universe. So from understanding the initial conditions and knowing how dark matter evolves, we can predict accurately the distribution of dark matter halos that we expect by, say, redshift of 0. And that's shown by the goal curve in this figure. And then we can compare this to the number density of luminous galaxies in the universe by stellar mass versus mass. And that gives us this black curve here. The normalization between them is just scales so they intersect at one common point. But the main thing to take away from this is that the two curves have different shapes. Now, if all halos in the universe contain the universal baryon fraction, and those baryons converted into stars at the same rate everywhere independent of mass, then we would expect these two curves to lie on top of one another. Obviously, they don't. And this means that star formation, the efficiency of star formation is scale dependent in terms of the halo mass. And we think this scale dependence is caused by feedback effects, which at the low mass end here are mostly due to stellar evolution and supernovae, and at the high mass end, mostly due to feedback from supermassive black holes. But this is problematic because we don't understand these feedback processes in detail, and understanding them becomes part of the solution that we're ultimately trying to obtain. So the ugly part about this in terms of actually arriving at a solution concerns feedback, because it means that we have to deal with an enormous range of scales, making the problem much more difficult. And so this is illustrated by these two images. The one on the left shows a starburst galaxy M82. There's a disk of stars here, and superposed on top of that, it's an image of gas that's being driven out of the galaxy from its center. So the fact that gas is being driven out means that the fuel to form further stars is being depleted, which means that star formation will be decreased by this outflow. And we think this outflow is the result of a bright starburst in the center of this galaxy throwing material out of it. The one on the right shows a more extreme example, Hercules A. It's a large elliptical galaxy at the center, and the pink image shows a radio map. In this case, the galaxy has relativistic jets emanating from a supermassive black hole at the center, terminating in these giant lobes in the halo of the galaxy. This has the potential to take energy from the center of the galaxy, deposit it into the gas in the halo, possibly inhibiting its cooling so that it can't accrete onto the galaxy to fuel further star formation. And so what this means is that these feedback processes couple the small scales to the larger ones. If things had been much more simple, if it had been the case that gas collapsed from larger scales to smaller scales, and there wasn't this feedback, then we could have separated the problem by scale, and that would have led to perhaps a solution decades ago. But the fact that all the scales are coupled, the small ones coupled to the larger ones, and the larger ones coupled to the smaller ones, means that we have to solve this problem simultaneously across all scales. On top of that, many of the processes that drive these feedback effects are not well understood. And what this means is that we are left with a nonlinear multi-scale problem that's essentially computational in nature. So this is to illustrate how severe the problem is in terms of the range of scales that we have to contend with. So ideally, we'd like to be able to simulate a volume which is close to the size of the observable universe, many gigaparsecs across. But at the same time, we'd like to be able to resolve the structure on, say, megaparsec scales, characteristic of groups and clusters of galaxies. and then down to kiloparsec scales that characterize the luminous distribution, stellar component, and gas component of individual galaxies. This is something we'd like to predict so we can compare it to what we see from observations. But ultimately, we have to account for processes on even smaller scales, in the most extreme case going down to scales of order 10 to the minus 3 to 10 to the minus 4 parsecs, characteristic of the scales in which energy is produced by these accreting supermassive black holes. Now, if you add up the total range in scales that you would need to solve this entire problem, then we're talking per linear dimension about roughly 13 or 14 orders of magnitude. The most efficient computational codes we have running on the fastest supercomputers in the world can at best do maybe 6 or 7 orders of magnitude per linear dimension. So per dimension, we're roughly 6 or 7 orders of magnitude short of being able to do this whole problem, which in 3 dimensions translates into a factor of around 10 to the 20th. This is currently impossible, and with existing computer technology, will always be impossible. And so we have to make certain compromises by truncating this range in scales, both at the large and small scales. So on the largest scales, rather than trying to simulate the entire universe, we're forced to simulate, say, representative volumes that are typically 100 or so megaparsecs across. And then on the smallest scales, we have to truncate this hierarchy roughly here, not explicitly allowing the simulations to follow the growth and production of energy from supermassive black holes, but those still need to be accounted for somehow because we know that they're critical for how galaxies evolve. And so what this means is that these small scale effects have to be incorporated into the simulations as sub-resolution models. So there are various approaches for carrying the sort of procedure out. I don't want to spend too much time on this, but basically the categories fall into either zoom-in simulations or large cosmological volumes, as I've illustrated in this nice review by Mark Vogelsberger. And basically it leads to a trade-off between the sample size and the number of objects that one can simulate and the resolution that can be achieved. And so the simulations I'll talk about today fall mostly into this category, large-scale cosmological volumes, where the resolution is certainly not approaching what you can do from say a very detailed zoom-in type simulation. But the benefit is that we can generate large samples of objects that we can compare statistically to what we see in the real universe. And so the two big projects that we've been involved with, we termed Illustrious and Illustrious TNG. You can find out about these in more detail at these two websites I've given here at the top. So these are cosmological simulations that account for the different components of the universe, the dark matter and the baryons principally, evolve with the moving mesh code, a repo that Volker talked about earlier. And we generate initial conditions that are consistent from studies of, say, the cosmic microwave background, from WMAP and Planck, as well as from type 1a supernovae. Now, the gas is treated as an ideal fluid, which is a good approximation on these scales, but we still have to account for other physical processes that govern how it affects and influences galaxy formation. Some of these are relatively well understood. For example, the way that the gas can cool and interact with ambient radiation fields. And at very high density, we have to allow the gas to be turned into stars so we can make predictions for the stellar distribution of the universe. Each stellar particle represents a stellar population that evolves according to fairly well-defined models. And furthermore, material which is produced from the stars, say mass, which is produced by stellar evolution on supernovae, can chemically enrich the environments, leading to the chemical enrichment of galaxies. Unfortunately, there are other aspects that are poorly understood and completely unresolved cosmologically. For example, the structure of interstellar gas and how star formation happens in detail. There we use the sort of sub-resolution model that Volker talked about earlier. We have to account for feedback from stellar evolution and supernovae and how that energy couples to the surrounding gas. Importantly, we also have to include supermassive black holes that are represented as collisionless particles in the centers of galaxies that can grow by accreting material and releasing feedback energy to affect their surroundings. And so the sub-resolution models are described in detail in these papers by Mark, Reiner, and Annalisa that I mentioned earlier. So the TNG suite consists of 3 different simulation volumes, 3 150 megaparsecs across, and I'll refer to these as TNG 300 and 150. The data from TNG 100 and 300 has been publicly available now for a while. TNG 50 was much more costly to carry out, and the data from that will become available next month in February. And so the different volumes allow us to probe different parts of the halo mass function. And furthermore, they achieve different resolutions, which allows us to look at things like numerical conversions. So this video is an illustration of the kinds of information that we can extract from these simulations. This is from Redshift 0 on the TNG 50 simulation. This is the projected distribution of dark matter at Redshift 0, the well-known cosmic web that Volker mentioned. This is the projected density of gas, which is highest in the high density regions where galaxies form. Right, the structure forms by gravitational collapse starting from the initial conditions that we prescribe. And then the dark matter settles into the dark matter halos that can cool to higher densities. This is the Lyman alpha surface brightness of these dense regions produced by cooling radiation from the gas. This is the temperature of the gas, which is cold in the high density regions and much hotter in their surrounding halos, and then very cool in the surrounding IgM regions. At sufficiently high density, the simulations allow the gas to turn into stars. This is the velocity field of the gas in projection. In the dense regions, the gas is either virialized or collapsing towards higher densities at the centers of the dark matter halos. This is the projected stellar distribution that we extract from the simulations that allows us to infer properties of galaxies and the surrounding stellar halos. And so rather than letting this go on, let me stop it here and move on to some of the scientific results. So this is just an overview of the sorts of things that the simulations have taught us over the past 6-7 years. So for example, from the illustrious simulation, and the result for TNG is similar, what we see at Redshift 0 is a population of galaxies that resembles that in the real universe fairly closely. So there are both star-forming disk galaxies, some with bars, some with spirals. There are non-star-forming spheroidal type galaxies that resemble ellipticals, and also irregular galaxies that are related to mostly galaxy mergers. And so if you look at the fraction of galaxies in each class, it's very close to what we see in the real universe, implying that if we start off with initial conditions prescribed by the cosmic microwave background and evolve them to Redshift 0 with these simplified models that we have, that they produce an outcome that looks like the real universe. Of course, there are approximations and assumptions involved in the modeling, and so one should be careful not to overinterpret the results. But if we use caution, I think we can use the simulations to understand properties of things that we see in the real universe that would be difficult to achieve otherwise. And so I wanted to give just a handful of examples of how the simulations can be used. This is from some work by a student named Kelly Blumenthal, where she used the simulations to study the properties of interacting galaxies, as shown in this nice plot produced by Annalisa Pilipich. So in the top row are some well-known real interacting galaxies that we see in the real universe. In the bottom are cases that are extracted from TNG 100 at Redshift 0, some of which closely resemble what we see in the images above. For example, this is the antennae, a well-known system of interacting disk galaxies, which closely resembles this object here that we see in TNG 100. And so this means we can use information from the simulations to construct idealized simulations of galaxy mergers that can then be used to, in more detail, understand what happens when two galaxies collide and merge. This is from work by Harvard graduate student Roxana Pop, These are galaxies known as shell galaxies, an example of which is shown in the upper left panel, NGC 3923. It's a giant elliptical galaxy surrounded by a concentric set of shells or arcs that are produced, we think, by mergers of galaxies. And so the images, the other 5 images, are examples drawn from the simulation that we've carried out, some of which closely resemble NGC 3923. For example, this one here. If you look at the number of these shells and the distribution with radius, it's very similar to what we see in 3923. And so because in the simulation we can track the evolution of these objects, we can go back in time and understand how an object like this one came about. And so what Roxana has done here is to identify at redshift 0 all the large elliptical galaxies in our simulation that have shells. And this shows the mergers that these galaxies experience through cosmic time. And in particular, the ones that are colored and filled in are the ones that gave rise to shell systems at redshift 0. And so this plot shows the relative velocity of the encounter and the mass ratio. The interesting thing is that the mass ratio of the encounters that produce the shells were all fairly large, approaching 1-to-1 for an equal mass merger. And in the past, it's long been believed that the mergers that produce the shells are mostly minor mergers with a very large mass ratio. But this suggests that that's not the case. And furthermore, we can use information from the simulations, additional predictions, to go out and test this idea. There are many other examples of unusual galaxies, like the so-called jellyfish galaxies that are seen observationally, like this one here in the upper left. See, these have been studied in detail by Annalisa Pilipich and collaborators. This is just one example that I'm showing in these 2 insets here. And then again, we can use as insight from the simulation to understand how an object like this came about. This is more recent work that I've been involved with the student at Florida, Zach Hemler, and his advisor, Paul Torrey and Lisa Cooley, where we look at gas phase metallicity gradients in star-forming galaxies. This shows one example. This is the metallicity of the gas versus radius. And the interesting thing here is if you look at the gas metallicity with radius, it has a negative gradient out to some radius, and then it levels out. And this sort of leveling out behavior is interesting. It's something has been anticipated in the work by people like Joss Bland Hawthorne. And in the simulations is connected to the fact that outflows from star formation cause gas to circulate through the halos of these galaxies and to be reaccreted in a more homogeneous way at these large radii. And so we can use the simulations to understand where these distributions come about and make predictions that can be tested observationally and perhaps to constrain how these simulations operate. This is from the work of Roxana Popp, where she's used the simulations to look at the properties of diffuse gas and halos, in this case through the Tsunami-Seldovich effect. It shows the Y parameter for the SC effect as a function of halo mass. And the interesting thing she finds is going from high masses to low massities, there's a break in this distribution at a scale characteristic to where the feedback processes go from mostly being AGN dominated at high masses to being dominated by star formation at low masses. And so if this sort of behavior is borne out by observations, we can use this sort of diagnostic as a way of proving feedback properties in galaxies of different masses. She's also looked at the diffuse X-ray emission from these halos. And I don't have time to go into this in great detail, but basically the results from TNG agree well with observations, whereas what we had from the original illustrious simulation shown by Red disagree fairly substantially. And that can be traced to differences in the feedback models that we've adopted. Let me just briefly show this. So in both sets of simulations, we have 2 different forms of feedback depending upon the accretion rate onto the central black hole. At high accretion rates, we imagine the black hole would be shining as a bright AGN or quasar, and that this feedback would be emanating as radiated energy deposited into the surrounding gas as thermal energy through photoheating. But we have to have a corresponding feedback process at low accretion rates to prevent quenched galaxies from becoming star forming again. So in Illustris, we imagine that this would occur through something like this radio motive feedback, where energy would be produced from the central black hole and deposited into the surrounding halo, possibly offsetting cooling in that halo gas and preventing it from fueling further star formation. Unfortunately, that had the effect of displacing gas from the halo outwards, giving rise to some of the discrepancies we see with the X-ray observations. So in TNG, we instead have a more localized form of feedback, perhaps similar to what is going on in these FR0 galaxies studied recently by Baldy and collaborators, where we see in this radio image from ALMA, this linear structure characteristic of jet-like activity, but on scales of not tens or hundreds of kiloparsecs, but more like 1 or 2 kiloparsecs. So the exact solution is uncertain at this point. We don't know if one or the other possibility is correct, some combination of these two, or something else entirely. And that still remains to be determined. So there are many uncertainties in the modeling. I don't have time to go into any of this in detail, but if there are questions about this, we can address this later. But in particular, these issues related to AGN feedback that still remain to be determined, prevent us from having a completely rigorous solution at this point. So let me just finish by just mentioning the past, present, and future of this field. So this is a field with a very long history with many important advances. They've led now to the state where the state-of-the-art simulations make predictions that can reproduce many observables, provide us with a framework for making testable predictions, but there's still many uncertainties and we don't have a full solution. So in the future, we hope to extend the simulations to larger scales. For example, we're doing simulations now illustrated like in this image on the right, which we call Millennium TNG, which is an extension of Illustris TNG to much larger volumes to make connection with ongoing and future high precision cosmological surveys. But to arrive at a full solution, we have to really develop a comprehensive theoretical modeling for these small scale theoretical processes that are so critical for determining how galaxies form and evolve. And so that will require us to ultimately arrive at more physical sub-resolution models, an endeavor that's likely to take many years or decades going forward. So thank you for your attention.
Thank you to both of our laureate lecturers. Let me now call on our discussion moderators. Wendy Friedman, the Sullivan University Professor of Astronomy and Astrophysics at the University of Chicago, and Martin Rees, the UK's Astronomer Royal and Emeritus Professor at Cambridge University. We are very fortunate that both of them serve as non-voting advisors to the Cosmology Prize.
Okay, can I start? Hello.
Yes, Professor Rees, you can go ahead with the first question.
Okay, well, the first question is from Alex Filipenko, who wants to know from Volker, I guess, how well do you think the correlation between a supermassive black hole mass and the sigma, the velocity dispersion, is understood now? Are there alternative explanations that are plausible? I guess this is for Volker.
Yeah, thanks. Very good question. So I think there is an alternative that has been conjectured, namely that this relation could arise from basically the central limit theory. If you have just many galaxy mergers and many black hole mergers, then you would also expect basically a correlation between stellar mass and black hole mass to rise, at least for the large galaxies. There are, I think, this predicts then differences in the scatter systematically across the galaxy size. And I think at the moment, at least my reading of the data is that the self-regulated growth model, where basically black holes size is limited by its own feedback radiation, for example, energy input, is a more plausible model, at least in my opinion. But I don't think the verdict is 100% out. There are still competing models that are pursued. I think the evidence is weighing in favor of the model that, akin to what we proposed through these simulations, but I wouldn't bet all my money on it, but a good fraction of it.
Thank you. Can I ask a question of my own, which I think is for either speaker? It's about the very, very small mass halos, which I guess Volker discussed in your simulations, going down to much less than the Earth mass. Is there any way of detecting those? I mean, the potential wells they produce won't affect the gas. I guess they will affect the annihilation rate if the particles annihilate, but would they be still around? And is there any other way in which we can check the cold dark matter model by looking for them?
Oh yeah, interesting point. Yeah, I mean, this limit, of course, what I described as Earth mass, this is arising as the thermal limit for a typical neutralino model, where you assume that the dark matter is made up of particles, say, of 100 GeV mass, which is the standard mass scale of the cold dark matter WIMP. Of course, there are other dark matter models, as you know, but this is still a pretty favorite model of many, even though we haven't found these particles yet. I mean, this mass scale is, as you said, it would be very, very difficult to predict. I mean, the dark matter would be relatively grainy. This graininess would be there mostly in the outer parts of halos. We still think that at, say, the solar circle, the halo most of the mass would be in a smooth component, but there would be a lumpy one left, extending all the way down to objects that are very diffuse but have Earth mass. I don't think they are very easy to detect, except for the indirect annihilation radiation. So yeah, this is a challenge. So you have a better chance to detect more massive objects, of course, through, for example, gravitational or perturbations they have on stellar streams and things. But at the smallest ones, I don't know an obvious way to find them.
There's a question from Simon White, which is, do you think it's going to be possible in practice to learn about the dark matter in any way by studying the properties of galaxies?
Well, that's easy, no? I mean, the rotation curves, for example, cusp core issue, if you, for example, I mean, I'm not saying it's easy, but the big debate we're having about cores in galaxies, if they are really confirmed, then maybe this rules out the classic cold dark matter model. And I would say this is one area, the detailed rotation curve shapes, long discussed about properties of galaxies. Then also if it's self-interacting, not collisionless, I would also expect the halos to be much rounder in the centers. That would impact the shapes of galaxies at some level, maybe the lensing efficiency. Yeah, those two would be some areas where, at least I think about the collisionality, you would learn something from the shapes of galaxies and the rotation curves.
So I seem to be experiencing some internet problems at the moment. If this lasts, I just wanted to convey my congratulations to both Lars and Volker, and thank you for your talks. The next question is from David Springel. In the coming decade, what will be the most important observations to test these models?
I think a lot of the cosmological surveys will be providing constraints at the potentially 1% level of precision. So I think that has the possibility of allowing us to constrain especially the feedback models that we've imposed in the simulations, particularly AGN feedback. by comparing the simulations, for example, the predictions that we can make for the X-ray emission from the halos, the ESC effect, particularly on large scales that intersect with the IGM. And given the accuracy of the potential accuracy of these surveys, they will have a lot of constraining power that we can use to leverage against the simulations, perhaps to understand better what the limitations of the modeling are.
Do you want to add to that, Volker?
Yeah, I mean, I agree. It's of course the question what aspect of the model you want to test. The AGN feedback, I think, is one of the most interesting one. But of course, in cosmology in general, we have, Wendy, you know this best. The H0 tension, for example. Whether there's evidence beyond the classic lambda CDM cosmology as we know it, maybe in the dark energy sector, say. And here again, I think the cosmological surveys will be the key. And they are very hard, of course, to uncover all of these effects, combined with other probes, like, for example, is the H0 tension real or not? The observers are working extremely hard on that by combining local probes with cosmological ones. That will be important. And then I'm personally convinced that the big galaxy surveys that are ongoing will, one way or another, hopefully bring out something unexpected, that brings us further. So I think it then, for David's questions, what aspect of the model we have of course different aspects there. The more the ones relating to the matter energy content, dark matter, dark energy, these are fundamental certainly, and then are the aspects of the physics modeling. And I think the AGN aspect is the hardest, but also galactic winds. We need to understand what drives galactic winds out of galaxies, because our simulations predict, for example, that the universal baryon fraction is basically not found, it's only found at the most massive galaxy clusters, and all the smaller galaxies manage at one point in their evolution to drive out a lot of baryons. And understanding that physics is, I think, still very hard. So observational determinations of the properties of galactic outflows across galaxy type and across cosmic epoch will be also key.
Yeah, I might add something else also. So observations by instruments like JWST will push the frontier of galaxy formation to much higher redshifts. And in our modeling, much of the constraints that we impose are gotten by observations at low redshift, which might not apply at much higher redshifts. So having observations at much higher redshifts that are very detailed in nature would allow us to test the uncertainties of our modeling in ways that is currently not possible.
And cosmic ionization
Maybe
is also exactly in this area where we'll get data from SKA, for example.
Maybe I'll also interject a somewhat related question from Hiranya Paris, who's asking what you think are the greatest discrepancies between simulations and observations, especially where you feel the physical modeling in the simulations is robust. This may be.
So, if I understood this correctly, the greatest discrepancies we face, I mean, the one thing I should maybe say, the TNG model, Lars described this nicely, is despite its simplicity, is I feel stunningly successful. So that is one huge surprise. How can you get away with such a simple model and broadly match so many observations? There are tensions here and there, but they are not glaring like they used to be, right? So you're a little bit off from some data, and you're not quite sure, is this very serious or not? Some people argue that on very small scales, the fact that in TNG, for example, we typically do not find huge cores in galaxies like sometimes inferred for dwarf galaxies, that is a serious discrepancy. But we, you know, this is an area where our modeling might not be so secure, so it's not falling into this category that was implied by the question. Lars, do you have anything to add here?
So the TNG model is certainly very good at reproducing many observables, but it's not perfect. So there are definitely discrepancies that we didn't have time to go into in this presentation. I wouldn't say that they're catastrophic, but there are definitely disagreements with observations, but they're mostly related to aspects of the modeling that are fairly uncertain, particularly having to do with how AGN feedback should be implemented in detail. So I would say that aspect of the modeling is not particularly robust at the current point. So it's not surprising that there should be some discrepancies with observations, even with how successful the overall model is.
Back to you, Martin.
Okay, well, the question from Jim Stone about whether you foresee machine learning and other data science approaches, the inductive method you mentioned, contributing more to the way structure formation simulations are performed in the future. And to be futuristic, may I add, there was another question about what quantum computing was going to do for this field. So I don't know if either of you wants to look ahead on those two issues, machine learning and quantum computing.
Well, I maybe let me first make a comment. I think machine learning is a fascinating technique, but it's praised by many as the panacea to all our problems. And so there I'm getting somewhat skeptical. So that's also my comment about deductive versus inductive approaches referred basically to this debate. So I still like the approach to writing down equations and trying to compute what they yield. So I do think that machine learning has huge advantages in creating mock data where you need it to sample large spaces in an effective way, and maybe also to accelerate in a convenient way certain nuisance calculations. For example, you might want to replace expensive nuclear network calculations or radiative cooling calculations, maybe with a quicker prediction of through machine learning to what is the cooling rate in a certain situation. And I can imagine this also as to act as an accelerator of some expensive simulations. But in the end of the day, I see them more as a powerful extension of our toolkit and not replacing the direct simulations.
Mm-hmm.
Julio Navarro is asking if these models of galaxy formation are falsifiable, or will there always be baryonic physics that could be argued to reproduce observations?
I would say that they're definitely falsifiable. So for example, the original simulation that we carried out, which we call Illustrious, was quite successful, but it failed spectacularly in a few cases. And particularly the disagreement that I mentioned with the X-ray luminosities of halos, especially at the high mass end. So based on that, I would say that the particular implementation of the model that we had there is falsified and is not acceptable because those observations are fairly accurate and easy to carry out. Whether or not what we have in TNG is closer to the truth is unclear. It's something that needs to be, considered further compared against more observations. But I would say that there are examples that you can point to where things just didn't work out the way that we had hoped. And so Volker may have some other thoughts about this.
Yeah, no, I think I could just more or less, I do think that there is real power in constraining models indeed. I mean, for a given model, you can sometimes not invoke just an easy escape. I mean, this is possible often, I agree, this is a problem, but not always. And the example Lars just described is one.
Could I ask a question of my own, which is an important limitation the actual complicated fluid mechanics, like mixing in shear layers and things like that. Everyone wants to know the distribution of heavy elements, how they get spread, etc. What hopes do you have of doing better modeling for the for mixing and magnetic fields and all that stuff?
Yeah, no, I think this is important, very important, but I'm somewhat hopeful that this can be done, because on turbulence and also the plasma physics, I mean, this relates to the scale challenge we have. But my idea would be that there is, of course, a lot of work done trying to understand the properties of turbulence, the properties of MHD turbulence, and also the effects of plasma physical kinetic effects on larger scales. And once we understand that better, the hope is to incorporate this into essentially analytic subgrid models that can be cast into modifications of the fluid equations on larger scales. Surely you have then an effective theory in this case, but by comparing to the more resolved calculation, I think one can hope, or maybe that one can even prove, that they still capture the physics that's relevant properly. So I think this is difficult, but seems with a lot of work doable to me.
Thank you.
I think we're out of time for questions. A huge number more we can't address, but we'll pass it back to Sarah Rera.
Thank you for a wonderful discussion. I myself enjoyed hearing familiar names from the questioners and seeing them in the Q&A section. And it's now my pleasure to bring on our closing speakers. These are just a very few special guests to end these proceedings on a personal note. First, let me welcome back the IAU president, Wien van Doschuk, along with Tim de Zoo, professor of theoretical astronomy at Leiden University, Observatory, to say a few words about Lars Hernquist.
Dear Lars, having attended previous Gruber Prize ceremonies, I know that the toast at the end of a sumptuous celebratory dinner, when most people are not fully sober anymore, are everyone's favorite part. Alas, here we are on Zoom with a sober virtual toast. But I do hope that you can enjoy these remote words. So warm congratulations once more with the Gruber Prize. I vividly recall our time together at the Institute for Advanced Studies in the late 1980s, when it was clear to me, not at all an expert in the field, that something special was happening in Fould Hall with you and Josh Barnes at the time. You were already laying the foundations for the new era of cosmological simulations. We subsequently met a number of times at Harvard in the decade following, most notably when I was chair of the Astronomy Visiting Committee. And I always appreciated your openness and your honesty in the discussions, including your warning about the limitations and not to trust everything that these simulations predict. And I think both of you have actually been very open and eloquent in discussing these limitations also here in the discussions. Lars, the impact of your work on our understanding of the galaxy evolution of the universe has been enormous, and you've paved the way for generations of young people in the field. A very well-deserved toast on behalf of all of us at the IAU to both you and to Volker.
Thank you, Evan.
My pleasure, Lars and Volker, to also congratulate you, and my burden to follow an eloquent speech by my boss here. Many congratulations. Lars, we were both at the same time at the Institute for Advanced Study as part of a group of postdocs which contained some truly colorful characters. It was quite a remarkable group, as you remember. You were fairly quiet, but we all knew that when your voice rose by maybe a fraction of a percent, this meant you were excited well into the Balmer lines. And that happened now and then. In this period, you laid the groundwork for what became a world-leading effort to simulate no less than the entire universe. I thought that would be a worthy ambition, and I'm sure that John Bacall would have been very proud with how it turned out. One unusual measure of success of the both of you is that observational astronomers now sometimes panic when their careful measurements do not match the outcome of the latest simulations. We've come a long way, huh? Your deep understanding of all the physics that needs to be included in the simulations luckily allows you to reassure them, as you indeed did in both of your lectures. Your open and positive attitude, Lars, combined with your talents as a wine connoisseur, have put you in a supremely excellent position to help guide the worldwide effort in simulations, especially those in, let's call them, strategic locations. A fine example is your role on the International Advisory Board of the Astro 3D Partnership in Australia, in which both of us serve, and where you constructively advised the Genesis simulation project centered in Perth, close to well-known wine regions. It would be very nice, as Evine has already said, to raise a glass to your success now in person, but we do so in spirit. Many, many congratulations to the both of you.
Thank you, Tim.
Thank you, Drs. Bishuk and Dessou. We got a 2-for-1 with them. They're in the same home. Let me now ask Carlos Frank, the Ogden Professor of Fundamental Physics and founding former director of the Institute for Computational Cosmology at the University of Durham, to say just a few words about Volker Springel. Dr. Frank.
Well, like Winnie, I wish I had something fizzy in hand, so we'll just have to make do with a symbolic toast. But of course, it's a great pleasure for me to have the opportunity to make a few remarks on the wonderful occasion of the award of the Gruber Prize to my friend and collaborator, Volker Springel, whom I have known since 1997, when he was a mere 27 years old, and to my also friend, Lars Hernquist, who I've also known since he was 27, which he achieved, in fact, 15 years earlier than Volker. Now, so I remember in 2009, Volker was awarded a prize called the Klung Wilhelmi Weberbank Prize, given to a German scientist under the age of 40. The organizer of the ceremony asked me to give the laudation, but he explained to me that the audience was a mixture of senior German scientists and bankers. The prize was given by a bank. And he told me that in Germany, such occasions tended to be rather dull, and that he had chosen me for my British sense of humor. Well, I took him at his word. The result, Volker didn't speak to me for weeks, but I should say that his lifelong and immensely supportive wife, Laura, she actually enjoyed the speech. Now, unfortunately, 2 minutes is not enough for me to offend Volker again, but it is enough to reiterate that Volker is the single most influential individual in the field of numerical cosmology. His contribution is unparalleled, from the development of the 2 most important and widely used computer codes in the subject, Gadget and Arepo, to the execution and analysis of 2 of the most influential cosmological programs ever, the 2005 Millennium Simulation, which is the most cited astronomy paper ever published in Nature, and the illustrious series of cosmological hydrodynamic simulations that we just heard about 10 years later. And I'm just reminded of when Volker was doing the Millennium Simulation. One day I had something to ask him, so I rang him. And so he picked up the phone and he was very agitated. He says, well, look, this better be important. And I said, why? Well, because I'm performing open heart surgery on the Gadget code. That is the way it was done in those days. But I want to say that Volker is not only a brilliant scientist, he's also a terrific person who is admired and liked in equal measure. He's sensitive, understanding, and generous. And for those of you who may think that his demeanor is rather serious, well, it is. But at the same time, Volker has really a dazzling sense of humor. So the award of the Gruber Prize to Hernquist and Springel merely confirms what all cosmologists know, that Hernquist and Springel are world-leading cosmologists who both, working together and with others, are responsible for key theoretical advances that have helped shape our view of the universe.
Thanks a lot, Carlos.
Gracias, Dr. Frank.
Thanks a lot.
And our final words go to our co-founder and President Emeritus, Patricia Gruber. Pat? It's been that kind of a technology day, I can attest to that. I'll give Pat 1 second to come back in, but while I shuffle for her remarks that I have backed up here. Did either of our recipients want to say anything?
Just thank you to the Gruber Foundation for your support and recognition. I really appreciate it.
Well, that for us is an honor and a pleasure. There she is.
Yes, sorry. I just wanted to add a personal note of congratulations to both of you, to Dr. Hernquist and Dr. Springel. As you probably know, your peers selected you with much rigor as well as much enthusiasm from an impressive field of other candidates. Your colleagues have sung the praise of your work, and we also congratulate you again. It's been 20 years since my husband and I sealed our collaboration with the IAU, and 10 since our agreement with Yale to continue these prizes. My late husband's wish to make a contribution that would leave the world just a little better than when he came into it, I think perhaps has been realized. And we're especially aware of that today with this award going to the both of you. We thank you both today for giving us science worthy of the very highest recognition. Congratulations.
Thank you very much.
Thank you very much.
Thank you, Pat. Everyone, please join me in applause to our recipients. Congratulations again to Lars Hernquist and Volker Springel. And thank everyone for attending. This concludes the 2020 Cosmology Prize.